In this video, we are dealing with 2.7 topic question number 9. There's the picture, you have the prompts in front of you hopefully, and what I'm focusing on is what we're trying to find. We want to find the minimum M2 that will cause the blocks to start moving. Key phrase, just like without slipping, key phrase is start moving, because if you start moving, start moving. Start moving means I'm not moving right now. That means my velocity is 0, but I'm going to accelerate, or I can accelerate, right? If I'm going to start moving, I'm allowing for a non-zero acceleration. Okay, what does that sound like? Kinetic or static? Static. Still no velocity, right? Now the other reason it's static, in this problem they kind of helped you out. They didn't give you a mu k. They didn't mention mu k. So kind of as an aside, this is more like test taking technique or prompt reading technique. The giveaway here was they only gave you mu s. If they only gave you mu s, or they bothered pointing out that there is a mu sub s, then you're already talking about static friction, right? So two ways to get to it. Non-thinking, oh, they didn't give me mu k, I must be talking about mu s. A little bit more thinking, I've got a situation where there's no velocity, but I have to be able to say I can accelerate. So we're in mu f, we're in static friction world. Okay. Minimum M2 that will cause the blocks to start moving. All right, well, let's just do free body diagram. I want to be able to point out the friction or recognize the friction there. But I have a system here where I've got the two, gravity is really acting on M2. So it's M2 is kind of controlling the strength of gravity, if you want to think about that, right? Because gravity is only pulling on M2. So let's do two free body diagrams approach, for starters. So let's do M1 first. Oh, some things to help out when you're doing Atwood's machine. You want to remember that if it's going to accelerate, the acceleration's that way. So when this thing accelerates to the right, this thing accelerates down, right? So if this is a positive acceleration, we have to think about that when we draw the free body diagrams. Okay, so for M1, I've got a tension force this way. I have a normal force that way, and then I have the weight of one this way, and then I've got static friction acting that way. On M2, I guess I'll just draw it here. So for M2, I have the weight of 2 and tension pulling up. Conditions for now that are almost taken for granted, but spring semester, all bets are off, and it may matter. The string has no mass. Why is that important? Well, then it we don't need a free body diagram for it. If it has mass, it's a free body diagram. The pulley can rotate without friction or slipping. In other words, the pulley has no mass as well. Otherwise, gravity is pulling not only the two masses, but it's got to pull hard enough to rotate the pulley. Okay, so the frictionless, massless pulley and string, very important. The frictionless pulley, important because if there's friction between the axle and the pulley itself, then there could be a torque. So just preview into spring. Torque is going to be a thing that causes friction, acts as a counter force or a counter torque. Okay, all right, so there's our free body diagrams. Okay, so let's just go, I'm going to skip all the, well, I'll go straight to Newton's second law. So for mass 1, we're going to go parallel to the table. Let's go, if this way is positive, then we've got T minus Fs has to equal the acceleration of 1a, right? I'm not zeroing it out because I might have an acceleration, or if it's going to start moving, right? And then I've got in the up and down direction, I'm going to have Fn minus W1. That's got to be 0. because there's no acceleration up or down. For M2, the only direction that matters is the vertical one, but which direction are we talking about with M2? M2 can only do this, right? But positive A is this way, which translates to positive acceleration for M2 down that way. So if I look at the forces for M2, I'm actually going to say this way is positive the way it's drawn. So I'm going to go W2 minus T has to equal M2 times A. They both will experience the same acceleration. So I'm just going to use the same acceleration value there. And the positive accelerations correspond to the exact same actual physical direction. So I'm going to use the same symbol, and I don't have to worry about positives and negatives anymore. Okay? All right. So what's the minimum M2 that will cause the blocks to start moving? All right, Newton's third law says what? Tension. Let's see. How could we do this? Why don't we just add the two equations? I happen to draw them vertically on top of each other. So I'm going to step aside so you could see what I wrote here. We've got that, right? If I add these two equations, you can see that I've got the t's will cancel, right? So this t minus t, 0. But I've got W2 because I'm adding them. So I'm adding these two equations. W2 minus Fs has to equal, if I add these two, M1 plus M2 times A. Or maybe I'll keep them separate, not sure. Okay, well, what's W2? W2 is just M2G. Now, if it starts moving, if it just starts moving, what does that mean? It also means I'm at the start moving. That means M2 is such that I've exceeded Fs max. In other words, if it starts moving, the friction force, right? If I load up M2, if I start increasing M2, I'm increasing this force. If I'm increasing this force and it's not moving yet, or it's not accelerating yet, okay, so I'm still increasing it, then the tension force is also increasing. This pull is increasing. So this force is getting bigger and bigger. If it's not moving, Fs can increase. Remember how static friction is a reactionary force. So Fs is increasing. Fs max. Fs is less than or equal to mu s Fn. So while T is getting stronger because of this weight, this Fs is increasing, but it's still less than mu s Fn. Fs can only grow up to a certain point, though. It can only be it can't get any larger than this, mu s Fn, that equality. So once this tension force is equal to that, then it's going to start moving. In fact, now that I'm looking at this was a nice exercise, but if you listen to what I just said, we could focus on this. Right? M1, blocks start moving. When the tension force on 1 is greater than Fs max. Well, what's the tension force on 1? The tension force on 1 is all this, right? M1 plus M2A. And actually at this threshold point, I wonder if that's basically enough. Because if it just starts to move, I just need that tension force has to be greater than Fs max, or it's at that tipping point, right? So when the tension is equal to Fs max, you know that M2, the minimum M2 is anything more than that. So if we look at, that's going to be mu s Fn, right? Which Fn? This one. Well, on this, I know I put an acceleration there, but if you look at this, when does this start to accelerate? Right? This guy will start moving when W2 is greater than T? Well, what's W2? W2 is just M2G. So let me pause this. When W2 is greater than T, right, then all that will play out. But this T, these T's are the same. So it's going to start moving when W2 is greater than Fs max, which is equal to mu SFN. Well, what's W2? W2 is just mg, m2g. So let me do this. Let me go to a different color so it's kind of easier to see. And we see that this is m2g has to be greater than mu s Fn. But what's Fn? It's just m1g. So what M2 do we need? M2 has to be bigger than mu s M1. And that is the video. Or that's the solution. Duh. I'm the video. That's the solution.